Okay, so we're going to work on differential equations, obviously. So the overview of the course. Yes.
Sorry, will the lectures be recorded?
Yes, I'm just recording it. Yes. And it will be posted on Canvas.
Okay.
So what we're going to do in this course is we're going to solve first order differential equations and second order differential equations. Okay? Higher order as well, but primarily first order and second order. So you're going to solve the first order differential equations using graphical methods, using variable separable, using method of integrating factors, using Laplace transforms, and using numerical methods. So you're going to learn 5 different ways of solving first order differential equations. Okay? You're going to learn how to solve the second order differential equations. You're going to use method of undetermined coefficients, variation of parameters, using matrices, using Laplace transforms. So you're going to learn 4 different ways to solve the higher order differential equations. There are like totally 9 kinds of problems that you're going to study in this 15 weeks. That's broadly it. Okay? So, and you're going to see some applications as well. Okay? You're going to see some applications. When we get there, I'll talk about it. So, because it is differential equations, it involves finding derivatives and finding integrals and dealing with matrices. And I'm sure you're good at it and you are done with it. So I have no issues with that. But these are some of the formulae that I expect that you will know. Okay? This is not exhaustive. This is some of the basic formulae that I would expect that you would know. Now, in this course, the notation is when I say y prime, I mean dy dt. That is y prime of t. And when I say y double prime, it's d squared y dt squared. And that also means y double prime of t. And when I say y triple prime, it is d cubed y dt cubed. And that is y triple prime of t. And so on. Okay? The Leibniz notation or Leibniz notation. That's notation that I'm going to use in this course. And ideally what we do is we introduce, let me experiment with you guys actually. So what is a differential equation? I'm going to go back and forth. Let me see how it works out. I don't know how it's going to work out, but okay, we're going to study only ordinary differential equations in this course. Okay, what is an equation? Anything that involves equal sign is an equation, right? What is ordinary differential equation? Ordinary differential equation is an equation with ordinary derivatives. What is ordinary derivatives? There is one dependent variable, there is one independent variable. Okay, that is what is ordinary derivative. And the equation that involves ordinary derivatives is ordinary differential equation. Is that clear? So in this case, is this an example of ODE? Yeah, because I can write this as 1 minus t times, d squared y dt squared minus 4t dy dt plus 5 times y is going to be cosine of t. So here the dependent variable is y. The independent variable is t, and the derivatives that I have are ordinary derivatives because the derivative is with respect to one independent variable t, so that's an ordinary derivative, and there is an equal sign in it, so it's an equation. So this is a ordinary differential equation. Is that clear? Or ODE. And the next problem is I can write this as t times d cubed y dt cubed, means y triple prime, minus dy dt plus y equals 0. Okay? So once again, I can see that the dependent variable is y, independent variable is t. I have ordinary derivative, meaning derivative of y with respect to one independent variable t, and so this is also an ordinary differential equation. Is that clear? And it has an equal sign, so it is an equation involving ordinary derivatives. So it is an ordinary differential equation. Now, what is not an ordinary differential equation? I will introduce that as the time goes by. But for now, this is what is ordinary differential equation. Is that clear? Are you all okay with that? The next thing I have is, okay, what is the order of the differential equation? Order of the differential equation is the highest derivative of the differential equation in the equation. So in here you see the highest derivative is the 2. So this is in this problem, highest derivative is 2. So the order of the differential equation is 2. So this is the second order ordinary differential equation. So this is called second order ODE. Clear? In this problem, the highest derivative is 3. Highest derivative is 3. Why? Because I have d cubed y dt cubed in the very first term. So that is the highest derivative. So highest derivative is 3. So this is the, here the order is 3. So this is the third order ordinary differential equation. Is that clear? Are you with me? Everybody okay? The next thing is, what is a linear differential equation? There are two different ways you can write a linear differential equation, but the more popular one is this, so I'll stick to that. So linear first order ordinary differential equation is y prime plus p of t times y equals q of t. Okay? So the coefficient of y prime is 1. P of t is the coefficient of y. Exponent of y is 1. And the right side is purely in terms of t. Does that make sense? The coefficient of y prime is 1. P of t is the coefficient of y. The exponent of y is 1. And the right side is purely in terms of t. If you can write a first order differential equation in this form, then it becomes first order linear ODE. If you cannot write it in this form, then it is a first order non-linear ODE. Okay? So now having said that, if I look at this problem, I have 4ty prime plus 5y equals cosine t. What should I do first? Say that again. Get rid of 4t. So you want to divide by 4t. In other words, you want to make the coefficient of y prime equals 1. So you're going to write y prime plus 5 divided by 4t times y is going to be cosine t divided by 4t. So the coefficient of y prime is 1. The p of t is going to be 5 divided by 4t. The exponent of y is 1. And the q of t is going to be cosine 4t divided by 4t. Cosine t divided by 4t. So you are able to write this in the form of y prime plus p of t times y equals q of t. So hence this is the linear first order ODE. Is that clear? Now what about this? Y prime equals y squared. You can see that the exponent, I mean you can try to write it in that form and stuff like that. But by just looking at it, the exponent of y is 2. The exponent of y is not 1, so I cannot really make it right in that form. So this is a non-linear first order ODE. Do you agree with me on that? Just by looking at it, I'm not trying to find out, okay, the coefficient of y prime is already 1. I'm not trying to find out what is my p of t. I'm not trying to find out what is my q of t. The reason being the exponent of y should be 1, but in this case the exponent of y is 2. So show and tell, look and tell. I mean you look at it and you say it is non-linear. Is that clear? Yes? Okay. Now the concept can be extended to what is a second order linear ODE, what is a third order linear ODE, what is a fourth order linear ODE. Why are we interested in it? One is so that we understand the nature of what is a linear differential equation. The other is because your web work will ask you questions like this. So for two reasons, we will want to work on problems like this. So your second order linear ODE will be y double prime plus p1 of t times y prime plus p naught of t times y equals q of t. Again, you can see that the coefficient of y double prime is 1, p1 of t is the coefficient of y prime, p naught of t is the coefficient of y, and the right side is purely in terms of t, not in terms of y at all. Does that make sense? And so on and so forth. Like if it is not in that form, then it will be a second order non-linear ODE. Okay? So now let's look at it. The problem is this. So first thing is you want to make the coefficient of y double prime equals 1. So you're going to write y double prime minus y equals negative t squared. So it is in the form of, okay, y double prime plus p1 of t times y prime plus p naught of t times y equals q of t. So if you compare the terms, the coefficient of y double prime is 1. You can see that p1 of t is 0 and p naught of t is going to be negative 1 and q of t is going to be negative t squared. So this is going to be a linear second order ODE. Is that clear? The coefficient of y double prime is 1, p1 of t is 0, p naught of t is negative 1. The right side is purely in terms of t. So that's why it is a second order linear ordinary differential equation. Clear? Now let's look at this problem. I mean, it is exponent of y is 2, right? Just how it happened in the first order. The exponent of y is 2. Here you see in here the exponent of y is 1, so it cannot be linear. So this is a non-linear second order.
Can you explain that one more time?
ODE. Which one, A or B?
B.
B. This is non-linear because, I mean, if I write this as y double prime minus y equals y squared, right? So this is in the form of y double prime plus p1 of t times y prime plus p naught of t times y equals q of t. You can see that p1 of t is going to be 0 and p naught of t is going to be negative 1. The coefficient of y double prime is 1. But q of t is y. Q of t means you are expecting that the function to be a pure function of t and not y, but on the right hand side you have y squared. That's why it's not linear, it's non-linear. You can do that, or you can just look at y and look at the exponent of y and say the exponent of y is 2, not 1, hence it's non-linear. Linear means line. So that's what it is. Are you with me in that?
Yeah.
Clear? Q of t is not a function of t, it is y squared, hence it is non-linear. Now the next one, number C, what do you think? What should be my first step? Divide by t squared, fantastic. So divide by t squared. So I write y double prime plus 1 over t times y prime plus 2 over t times y equals sine t over t, right? So you can look at it and say, okay, p1 of t is going to be 1 over t, p naught of t is going to be 2 over t, and you have a q of t is going to be sine t over t, and hence it is a second order linear ODE. Clear? Are you all good? Yeah.
2 over t squared sine t over t squared, right?
Could you repeat that again, please? Oh, 2 over t squared, yes. Yeah, thank you. Thank you. Are you all good with that? So what about D? Is it linear or non-linear? Why is it non-linear? So is it okay if I just say it is non-linear and don't need to write out everything? So this is the non-linear second order ODE, right? Clear? Okay. So the next thing is, okay, now I introduce what is a differential equation. Any equation involving derivatives and equal sign is differential equation. What is ordinary differential equation? It is a differential equation with ordinary derivatives in it. What is ordinary derivative? There is one dependent variable and one independent variable. What makes it ordinary is one independent variable. If you have two independent variables, then it becomes partial. Are you with me on that? For those of you who have taken 2551 already, you know what is partial derivatives. That means there are two independent or more than one independent variable and one dependent variable, right? So ordinary derivatives inside that, so it is called. So once we know what is an ODE, then we wanted to discuss what is linear and nonlinear, linear and nonlinear first order, linear and nonlinear second order. We did that, right? So now let's go back to what section 1.2. Now that we introduced the terminology, let's go back to the this. So what is the first order? You know what is first order? The derivative is highest derivative is 1. Autonomous differential equation will be of the form y prime t equals f of y. So this is in the form of y prime equals f of y, which means the right hand side has no t in it. The right side is only a function of y. Right hand side has no t in it. Y prime equals f of y. It is first order because the highest derivative is 1. It is an equation because there is an equal sign. It is an ordinary differential equation because there is only one independent variable. And it is autonomous because the right hand side is a pure function of y. It has no t in it. Is that clear? If there is a t on the right hand side, then it becomes non-autonomous differential equation. Okay? So let's look at few examples before we get to it. So I have y prime equals cube root of y. So this is in the form of y prime equals f of y. Right hand side has no t in it. Right? So that's why, is it autonomous or non-autonomous? Autonomous, right? Autonomous differential equation. First order differential equation. Is that clear? Now a question, is it linear or non-linear? Non-linear. Why is it non-linear? Because of cube root, right? Okay, the next one is you have y prime equals y squared. So this is again in the form of y prime equals f of y. Right hand side has no t in it, right? Has no t in it. So is it autonomous or non-autonomous? Autonomous differential equation. So is that linear or non-linear? Non-linear. Why is it non-linear? Y squared, right? So now let's look at this problem. This is in the form of y prime equals f of ty. Do you see that? So right hand side has a t in it. So is it autonomous or non-autonomous? Non-autonomous, right? So this is non-autonomous differential equation. Is that linear or non-linear? Non-linear. Why is it non-linear? What is linear? Linear means we should have it in the form of y prime plus p of t times y equals q of t, right? Is it in that form? Because in the linear one, there is no y in the denominator. This one has a y in the denominator. That's why the coefficient of y prime equals 1, and there is a y in the denominator. That's why it's non-linear. Okay. Now the next one is, okay, this is y prime equals t squared plus y squared to the 2/3. So this is in the form of y prime equals f of ty. Okay. Right hand side has a t in it. So is this autonomous or non-autonomous? Non-autonomous differential equation.
basically, if there's a T on the right-hand side, then it's non-autonomous.
Right. And if the absence of t means, see, you have to make the coefficient of y prime equals 1. That's the first step. After you make the coefficient of y prime equals 1, if there is no t on the right hand side, then it is autonomous. Because I can trick you by doing this, t y prime equals y squared. Right? So right now, then the first thing you want to do is, okay, I want to write y prime equals 1 over t times y squared, and this is in the form of f of ty, so this is non-autonomous. So you have to make the coefficient of y prime equals 1 first. Whether it is, see that the same thing happened in linearity as well. You have to make the coefficient of y prime equals 1 first, and then you can decide whether it is linear or non-linear, or autonomous or non-autonomous. Yeah.
Could you explain why A is nonlinear again?
This is this one, the ty prime equals y squared.
No, A, the first one.
A. It is non-linear because the denominator is 2t plus 5. Okay, one of the ways, there are multiple ways you can explain it. One way is I cannot write it in the form of y prime plus p of t times y equals q of t. I cannot write it in that form. And that's why it's non-linear. Number one. Number two, if you look at it, you see the exponent of y is 1 here and y is in the numerator. Whereas here the y is in the denominator, and that's why it's non-linear. You can look at it and say that because y is in the denominator, let's say if I'm able to bring out y onto the top, the exponent is going to be negative, so that's why it's not linear. Are we all together on this so far? Okay, so remember I said a few minutes ago, we're going to solve the first order differential equations using geometric methods, using variable separable, using method of integrating factors, Laplace transform, and numerical methods. So the first one I said was I'm going to solve it using graphical methods. So I'm going towards that, and that's where this is all coming in. So now, what are equilibrium points? Equilibrium points are also referred to as critical points, fixed points, or stationary points. And you know what are critical points from your knowledge of calculus. What are how do you find critical points? Set the derivative equal to 0, right? So what happens at critical points? What is something special about critical points? Yes, go ahead. Derivative is 0. What does that mean?
Maximum and there's no change.
Say that again.
Maximum and minimum. Or solid.
So do you always have a maximum and minimum at the critical points? Not always, right? Can you think of one function which has a critical point but does not have a maximum or a minimum at that point? What is it? Y cube, right? So that's what is a critical point. I just wanted to, now that we are talking about critical point, just wanted to bring it out. Okay. So if I have an autonomous differential equation, y prime equals f of y, and I want to find a critical point or equilibrium solution, I'm going to set y prime equals 0, right? To find critical point or equilibrium solution or fixed point or stationary point. So when I set y prime equals 0, I'm really setting fy equals 0, right? And I'm going to solve for y. Solve for y to find critical points or stationary points or fixed points or equilibrium solutions. Is that clear? So what am I going to do? Once I find out, I'm going to my goal right now is I don't want to solve the differential equation. I'm going to use some kind of increasing, decreasing, concave up, concave down, and try to graph the solution of the differential equation without really actually solving it. Does that make sense? The process is I have a differential equation, I find the solution, I graph it. That's the process, right? But now I'm trying to see, okay, in my autonomous differential equation, can I find critical points use my increasing, decreasing nature, use my concavity of the solution, and graph it without actually solving it. Do you see where I'm going with this? So I'm not really solving the problem, but I want to be able to at least provide the rough sketch of the graph. Clear? Okay. So with that said, so when I graph the solutions, I'm going to have few things. One is, if you call this as a t-axis, and this as a y-axis. So let's say I get one critical point, y equals y1. I'm just giving you what are the possible scenarios before I actually go about solving it. When I find a critical point, let's say I get one critical point, y equals y1. I can have four scenarios. One is, all the solutions converge to my critical point, like how this is happening here. So for all the y values bigger than y1, the solutions are decreasing and converging to y1. For all the solutions less than y equals y1, the solutions are increasing and converging to y1. Is that clear? That's scenario number one. If that happens, then we are going to say y equals y1 is an asymptotically stable equilibrium solution or asymptotically stable critical point. Okay? Scenario number two. I have an autonomous differential equation. I find a critical point. I get my critical point y equals y1. Then the second scenario is, for all the values of y bigger than y1, my solution is going to move away or diverge from my critical point. For all the values y less than y1, my solution is going to diverge and move away from my critical point. So the solution curves are going to go to infinity for y greater than y1 and going to negative infinity for y less than y1. And such a critical point is called unstable equilibrium solution or unstable critical point. Is that clear? That's a scenario number two.
Is the first one also called unstable?
Asymptotically stable. The first one is asymptotically stable. The second one is unstable. Okay? Now, how do you demonstrate it? On the phase line, when it is converging to y1, I'm indicating the arrows like this, indicating that my solutions are converging to y1. That's how I represent it on the phase line. Okay? On the phase line, the second scenario can be represented on the phase line like this. That means all the solutions are moving away from the y1. Okay? The third scenario is, for all the y values bigger than y1, the solution is unbounded or moving or diverging from y1 or moving away from y1. For all the y values less than y1, the solution is converging to the critical point. So on one end, like it is converging to y1, on the other end, it is moving away from the y1. Does that make sense? Clear? So such a critical point is called semi-stable equilibrium solution or semi-stable critical point. So for certain values of y, you are going towards the critical point. For certain values of y, you are going away from the critical point. Make sense? Hold these thoughts, because when you see the applications, at least some applications, you will realize the importance of them. I don't want to bring in too much at one point, so I'm just introducing the theory for you now. The fourth scenario is the other way around. I mean, for certain values, you converge to the critical point. For certain values of y, you diverge from the critical point or you move away from the critical point. So that means you're moving, for all the y values bigger than y1, you're moving towards the critical point. For all the y values less than y1, you're moving away from the critical point again. So y equals y1 is semi-stable equilibrium solution or semi-stable critical point, or semi-stable fixed point, or semi-stable stationary point. Make sense? So we have, what am I doing? I have the first order autonomous differential equation. The process is I solve it and then I graph the solution. But now I'm trying to skip solving it. I'm trying to find my critical points, use my increasing, decreasing nature, use the concavity, my knowledge of concavity, to graph the solution without actually solving it. Clear? And I will come up with 4 scenarios. One scenario is where all the solution curves are converging to the critical point, asymptotically stable, where all the solutions are diverging away from the critical point, where for certain values of y you're converging to critical point, for certain other values of y you're diverging from critical point, and hence that critical point is called semi-stable equilibrium point. Clear? These are the 4 scenarios. That's an introduction to it. Now once you were introduced to the concept, now you know what you're going to do. You're going to just solve the problems and then prepare for the quiz and the test, right? So here is the problem. So y prime equals e to the y minus 1. What is the order? What is the order? First order. What is the dependent variable? Y. Is it linear or non-linear? Non-linear. Why is it non-linear? E to the y, right? So is it autonomous or non-autonomous? Autonomous. Why? Because there is no t, right? So we're going to go for, so the way we're going to do is we're going to find critical point. We're going to use the test point method to sketch the phase line. Then you are going to classify the critical point, and then you're going to sketch the solution curves, sample solution curves. Meaning they're not actually, they're not correct to the scale, but at least you're trying to give some geometry to it. Are you with me on that? So first thing is you want to find the critical point. So how do you find the critical point? You set y prime equals 0. In other words, y prime is f of y is 0. F of y is e to the y minus 1 equals 0. So you get e to the y equals 1. So what is y? Y equals 0 is the critical point or the equilibrium solution. Is that clear? So now the question is it asymptotically stable? Is it unstable? Or is it semi-stable? Right? So we want to use the test point method and decide on that. Okay? Now let's say, okay, my y prime equals e to the y minus 1. Just for the heck of it, what is y double prime? Very good. Keep that in mind. So now I'm going to use the test point method. So I'm going to say for y equals 0 is the critical point. So for some y less than 0, so I want to pick a candidate. So I'm going to pick y equals negative 1. So when y equals negative 1, my y prime is going to be, what is that? My y prime is going to be e to the negative 1 minus 1. Is it going to be positive or negative? Negative. Very good. So that means, is my function increasing or decreasing? If the first derivative is negative, is it increasing or decreasing? Decreasing, right? Okay, then what about my y double prime? So my y double prime of negative 1, is it positive or negative? Positive. So is it concaving up or concaving down? Concaving up. Okay, keep that in mind. So for some values of y bigger than 0, what value should I pick? 1. Okay. So y prime is going to be e to the 1 minus 1. Is it positive or negative? Positive. So my solution, is it increasing or decreasing? Increasing. So what is y double prime of 1? Is it positive or negative? Positive. So this is concave up. This is concave up. This is decreasing. And here it is increasing. Do you agree with me on that? So, but the phase line has nothing to do with concavity. The phase line has to do with only increasing and decreasing. So I'm going to draw the phase line like this and say, maybe I'll erase this so that you don't get confused. The phase line is, I have y equals 0. So it is decreasing before 0, it is increasing after 0. Do you agree with me on that? So my solutions were moving away from my critical point. So what is the classification? Is it unstable, asymptotically stable, or semi-stable? Unstable. Very good. So you're going to say y equals 0 is unstable. Critical point. Do you agree with me on that? Now, I did not solve it. Do you agree? I had a first order, non-linear, autonomous differential equation. I did not solve it, but I'm trying to sketch the graph of the solution, rough sketch of the graph of the solution, right? So now how do I proceed? I mean, okay, now I'm going to say this is my y-axis, that is my t-axis, so this is y equals 0. What I got was it is decreasing in concave up and it is increasing in concave up. Do you agree with me on that? So like that. So increasing in concave up means how does the graph look like? From your knowledge of calculus, it looks like that. Do you agree with me? Decreasing in concave up means from your knowledge of calculus, it looks like that. So that is going to look like, that is the rough sketch of the solutions for this differential equation. So you actually did not solve it. You don't know the solution, but using the, this is called qualitative behavior. Using the qualitative behavior, you are able to graph the solutions of the first order nonlinear autonomous differential equation. Is that clear?
What does plus and minus plus mean?
Oh, this is increasing and this is concave up. This is decreasing and this is concave up. Yes.
Is the bottom one drawn concave down?
You're right. I drew concave down, right? Did I get the concave up there as well?
I think it's concave up, yeah.
So how does the concave up look like? Decreasing and concave up, how does that look like? I have 4 ones, right? Increasing and concave up, increasing and concave down, decreasing and concave up, decreasing and concave down, right? So how would it look like? It would look like something like that. Right? Do you agree with me on that? Thank you.
Unstable though.
Say that again.
If it's unstable, then it's supposed to be concave down. Either one.
It's unstable because it is, see, stable or unstable doesn't have anything to do with concavity. The solutions are moving away from the critical point, that's why it's unstable. It has nothing to do with concavity. Make sense? Clear? Are we all together on this? Okay, the next one is y prime equals y times y minus 2. I have y prime equals y times y minus 2. So I want to find this. I'm going to repeat the process. I'm going to find the critical point. I'm going to sketch the phase line using the test point method. Then I'm going to classify the critical points. And then I'm going to, after classifying the critical points, what am I going to do? I'm going to graph the solution curves. Right? So now, to find the critical point, I'm going to set y prime equals 0. In other words, I'm going to get f of y equals 0. Correct? When I set f of y equals 0, I'm going to set y times y minus 2 equals 0, which means I'm going to get either y equals 0 or y equals 2. Right? So I have multiple critical points, y equals 0 and y equals 2. So the next step is I want to use the test point method to find out whether my solutions are increasing or decreasing on certain regions. Is that clear? So for that, I'm going to say, okay, first region is y is less than 0. Then the next one is 0 is less than y is less than 2. The other one is y is bigger than 2. So now when y is less than 0, I'm going to pick y equals negative 1. So I get y prime is going to be negative 1 times negative 1 minus 2. So that's positive. So that means that my solution is increasing. Do you agree with me on that? Yes? So I want to pick a value for y between 0 and 2. I'm picking y equals 1. So when I pick y equals 1, I get y prime equals 1 times 1 minus 2. So that's going to be negative. So my solution is decreasing when y is between 0 and 2. So what happens when y is bigger than 2? I want to pick y equals 3. You can pick any value, but I'm picking y equals 3. So y prime is going to be 3 times 3 minus 2. So that's positive. So my solution is increasing for all the values of y bigger than 3. Right? So how does my phase line look like? Okay, now my phase line looks like, you see my phase line has nothing to do with concavity. I just introduced it so that you can see the shape of the graph, but my phase line has nothing to do with the concavity. So I have y equals 0, y equals 2. For all the values of y less than 0, my solution is increasing, so I'm going to put it like that. It is increasing and going towards y equals 0. Agreed? For all the values of y between 0 and 2, my solution is decreasing, and when it is decreasing, it is going to y equals 0. Right? Clear? For all the values of y bigger than 2, my solution is increasing, so it is moving away from y equals 2. So once you draw the phase line like this, you're pretty much set for classification, right? So y equals 0, how do you classify it? Is it asymptotically stable, unstable, or semi-stable? Asymptotically stable. So you are going to say y equals 0 is asymptotically stable critical point. And what about y equals 2? The solution curves are moving away from y equals 2, so y equals 2 is unstable. Very good. Clear? Now with this knowledge, you want to graph this solution, rough sketch of the solution curves, right? Okay, that's what gets really interesting. Let's see how we proceed through that. This is rough sketch. So now y equals 0, and this is y equals 2. Y equals 0 is asymptotically stable, so they are moving towards that. And y equals 2 is unstable, so the solution curves are moving away from that, right? Are you with me on that? So now, how would the solution curves look like this? I mean, as t goes to infinity, the solution curves are going towards that. Do you agree with me on that? Like, it's going to be like that. Do you agree? So before that, I mean, you can draw a curve like that. Agree with me on that? So what did I do? I drew something that is concave down and increasing. Do you agree with me on that? So if you find the second derivative, I mean, y prime is going to be y squared minus 2y. So y double prime is going to be 2y minus 2. For all the values of y less than 0, it's concave down. So I will get concave down and increasing. So my solution curve would look like that. Are you all okay with that? Yes? Should I repeat it again?
How do you determine the concavity again?
Concavity is from the problem tells me y prime is y times y minus 2. So y prime is y squared minus 2y. So concavity is from the second derivative. So I differentiated one more time. When I got it wrong here. The derivative of y squared is 2y times y prime. And the derivative of negative 2y is negative 2. Do you agree with me on that? So now if you check it for any value of y less than 0, it is going to be concave down. Plug it in and see. Okay? So now what is going to happen here is the same thing is going to happen here. Now, my solution curves are going to be because they're converging to y equals 0, it is going to be here. At y equals 2, it is moving away from this. So what happens? In the middle, I'm not doing the computation, but it starts very close to y equals 2 and changes its concavity and converges to y equals 0. It can be established mathematically, but I'm not showing it to you right now, but that's the way you can, this is a qualitative behavior, so you can do it like that. Is that clear? I'll repeat this again. If you want to hear it one more time, you can hear it. If you don't want, it's okay. So as the time goes to infinity, my solution curves are converging to y equals 0. So I'm getting close to y equals 0. But when I start out from y equals 2, I'm decreasing. So I change the solution curves, change its concavity and converges to y equals 0. That's the only way it converges to y equals 0. If it doesn't change the concavity, it doesn't converge to y equals 0. You can establish that using, the derivative and all that. But I'm not just, y equals 1 will be the critical point. It changes the concavity at y equals 1. And you can sketch the graph and you will see that it changes the concavity at y equals 1. And it will be decreasing and concavity changes and it converges to y equals 0. Is that clear? Are you all okay with that? Okay, now what happens at y equals 2? At y equals 2, it is moving away from the critical point, so it's going away from y equals 2, and that's how my solution curves look like when I go there. I have two things. It's okay, but one is that, remember when the independent variable is t, when you find the second derivative, it's not 2y minus 2, it is 2y times y prime minus 2. It's a chain rule. Number one is that, okay? And number two is I need to go back to the previous problem and change something else. Now I want to.
For the middle section, how do you know that it starts at y equals 2 instead of starting down at y equals 0?
If it starts at y equals 0, is that what you're saying?
Yeah, and then it goes up.
It cannot start at y equals, y equals 0 is what? It's a critical point, right? So if it starts at 0, it stays at 0. Because there is no change. Y prime is 0, there is no change. If it starts at 0, it stays at 0. But if it starts, let's say, now let me pick a different color. Let's say if it starts here. Then it goes like this and changes its concavity and goes like this. Make sense? Are you all with me on that? Now what I want to go back and change is this. So if you look at y prime is e to the y minus 1, what is y double prime? E to the y prime, right? So for any value of y less than 0, in other words, y equals negative 1, what happens? Y double prime is going to be e to the negative 1 times y prime. Below that is going to be negative, right? So this is going to be a negative quantity, right? So it is decreasing and concave down. Do you see that? So it's decreasing and concave down. So that I forgot y prime there. So that's why that curve looked like that. It's decreasing and concave down. So it just goes down like that. Is that clear? Make sense? In the heat of the moment, I just forgot my chain rule, so because of which I messed up my shape of the solution curve. My phase line was not affected, but my shape of the solution curve was affected. Clear? So one more time, I'm repeating it. We want to solve the first order differential equation, find the solution, right? First order differential equation, find the solution, and then graph the solution curve. So what we are doing is we are studying the qualitative behavior. We are finding the critical points, we are drawing the phase line, and then we are sketching the solution curves, the rough sketch of the solution curves without actually solving it. That's what is meant by studying the qualitative behaviors. Is that clear? Okay. So then the next one is that y prime equals y squared times 4 minus y squared. So now what are we doing? We're doing the same thing but increasing the complexity. So first step is find critical point. Step 2 is use the test point method to find the phase line. Step 3 is, you grab the solution curves. Oh no, classify it, classify the critical points. Step 4 is to sketch the solution curves.
What's the name of the method?
Test point method. There is no name like that. I just use it because that's how I studied it. Okay, it's not really a name. Sketch the solution curves. Right? So, I mean, when you say set y prime equal, to find the critical point, you set y prime equals 0. So you're going to set f of y equals 0. So you set y squared times 4 minus y squared equals 0. So you get y equals 0 and y equals -2 and y equals +2. So these are your critical points or the equilibrium solutions. Is that clear? These are your critical points or equilibrium solutions. Clear? Everyone okay? So once you find that, okay, you want a phase line. So what happens was, you want to use the test point method and sketch the phase line. So you have y equals -2, y equals 0, and y equals +2. So for values of y less than -2, the y prime turned out to be negative. So you get it like that. Is that clear? I'm skipping the computation because I've done it twice. I'm pretty positive that you can repeat the process. So I'm just skipping the computation and just giving you the conclusion. Clear? Then when the y value is between -2 and 0, y prime is positive. That means the solution is increasing. So that means it's moving away from y equals -2. Is there anyone who wants to see the computation, or are you comfortable with me skipping it? You want the computation? No, you're fine. Okay. So when the value of y is between 0 and 2, you can see that y prime is positive, so that means it's moving away from y equals 0. When for all the values of y bigger than 2, y prime is negative, so that means you're going back to y equals 2 or converging to y equals 2. So you can see that the solution curves are moving away from y equals -2. Solution curves are converging to y equals 2. And for certain values of y, the solution curves are going to y equals 0. For certain values of y, the solution curves are moving away from y equals 0. So the classification is y equals -2 is unstable, y equals 0 is semi-stable, and y equals 2 is asymptotically stable, right? Everyone okay with that?
Yeah.
Okay, so now you want to sketch it. The rough sketch would be so -2 was unstable, right? So unstable means I get that. And 0 is semi-stable, and y equals 2 was asymptotically stable. Do you agree with me on that? Now, I'm really not, you can really evaluate the inflection point, and I think they will turn out to be zero plus minus 1 over square root 2, I think. And you can check all the concavity and stuff like that. But if I were to skip the computations and give the rough sketch of the solution curves, so if my solution begins here, it's diverging from y equals -2, so it goes like that. Are you with me on that? If my solution begins here, so that means my solution is diverging and it goes away like that. Is that clear? Now, if my solution is here, if it begins here, see, you see, it should move away from y equals -2, but it should converge to y equals 0. So it goes like this and changes its concavity and then converge to y equals 0. Does it make sense? Using the same logic of the previous problem. Clear? So between 0 and 2, what is happening? If my initial value starts out from here, it should converge, If my initial value starts out here, it should start from here and it should converge there because y equals 0 is semi-stable, so it changes its concavity and goes there. Right?
Does it always change concavity for semi-stable?
You see, the very first problem, we did not have it. I mean, the concavity did not change in the very first problem. But in here, it is changing. So it's problem specific. You cannot say it is one way or the other for all the problems. And within the same problem, the concavity is changing as well. So it's problem specific. Now, for y equals to, for all values y bigger than 2, the solution converges to y equals 2. So that's how the solution looks like. So once again, we had the first order nonlinear autonomous differential equation. Just using the critical points and the qualitative behavior, we try to graph the rough sketch of the solution curves without really actually solving it. Yes?
So between y equals 0 and y equals 2, how do you know that it definitely has a switching concave and not just like increasing concave down?
One is, like I said a few minutes ago, mentally I looked at what is y prime is 4y squared minus y4. So y double prime would be what? 8y minus y to the 8y minus 4y cubed. So computation would tell you that y equals 0 and y equals plus minus 1 over square root 2 are the possible candidates for the inflection point. Then you have to see if it changes the concavity or not. Okay, so in this case, but the main question is in this case, when the solution begins very close to y equals 0, it is moving away from y equals 0. So that means it's diverging away from y equals 0. Okay, and but y equals 2 is a critical point, so that means it should converge to y equals 2. So the only way it happens is when it changes concavity in the middle somewhere. So I'm really saying that without doing any computation, and I'm saying it based on the computations that I have shown in the previous problem, the similar thing can be done. Is that clear? Okay. That finishes this lecture. So if you have no questions, you can leave me.